2.4 is about the chain rule. And what a chain rule allows us to do, is find the derivative of a composition of functions. So we've learned how to do the derivative of a sum and difference. How do you do the derivative of a sum of functions and a difference of functions?
The derivative plus the derivative.
You do them each separately, yeah. Yeah. So if you want to derive f plus g, you do f prime plus g. So that's sum and difference. Those are easy. For product and quotient, we got a rule. Chain rule talks about composition. So when you have one function composed with another or one function plugged into another. So I'm going to start us off with a couple of, before I actually give you the rule, we're going to do some pre-calculus. Just as a review. So the instructions here, just to get us warmed up, decompose each function into an inner function which we're going to call g of x, and an outer function f of x. Let me show you what I mean. So I'll give you a function, h of x equals, start with 2x plus 1 quantity cubed. And what I want you guys to do is take this apart, okay, find me an f and a g such that when you plug g into f, it equals h. That's what decompose means. Figure out these starting functions that you can use to build this. There's never one answer to this. Okay, there's always infinite number of answers.
2x plus 1, 3x.
Right. Oh, not 3x. Close.
3 cubed.
X
Or
cubed.
X cubed.
Right. So the way you want to think about this is the inner function is 2x plus 1 because that's on the inside somewhere. And the outer function, because of this cube here, is going to be x cubed. So what I would say is f of x has, well, it doesn't have to, but one choice for f of x is x cubed, because that's the outer function, and then one choice for g of x would be 2x plus 1. Because if I plug this into here, I would get this. And this is fantastic from a calculus point of view because we don't actually know how to take the derivative of this, but we do know how to take the derivative of each of these. Okay, so we're going to be simplifying our problem by breaking a composition into its component functions. Yes? Well, what do I have to do to this to get this final answer? All right, what do I have to do to 2x plus 1? What operation do I have to do to 2x plus 1 to get 2x plus 1 cubed? You have to cube it. Now the x is just a placeholder. So the x is just holding the place of this guy which we're going to plug in when we check.
So pretty much x equal to x plus 1.
When we plug in, yes.
Finish.
Yes, x will be replaced with 2x plus 1. So what about h of x equals root 1 plus x? What's the obvious way to decompose this?
X squared, x plus, or 1 plus
Root x.
So the inside is 1 plus x, and the outside is root x. Does that make sense? So g of x would be 1 plus x, and then f of x, the outside, would be root x. Because if you plug this into here, you get this. And again, both of these we can differentiate, while this guy we haven't learned how to differentiate. But we will. See if I can give you a slightly trickier one. Sine 2x the inside and outside function?
Um,
If I wrote it like this, would it help?
Just a constant.
2x.
So in this, this is what sine of 2x means. It means the 2x is inside of the sine function.
So f the x is 2x and g the x is sine.
Well, other way around the way that I have it written, but yeah, other way around. The outer function is sine.
Mm-hmm.
The inner function is 2x. Right, the 2x is inside. And sine test. If I plug this in here for x, then I'll get this result back.
Mm-hmm.
Okay, so that one's a little more, slightly less obvious. This one's going to be probably obvious now that we did that one, I hope. Sine of x squared is my original function. I want to decompose it. Yeah, so the inside function here, again, you want to think of parentheses around this guy.
Mm-hmm.
So g of x will equal, the inner function will equal x squared. The outer function will once again be sine. Now here's the one that you guys have trouble with.
It won't just do sine x times sine x.
Well, yeah, but that doesn't do this.
Oh.
So this is sine x times sine x, but that doesn't help me decompose this into an inside and an outside. However, thinking of it like this does. Right, this is really sine of x
Oh.
squared. Right?
Mm-hmm.
So x squared and sine.
Right, but not like this. It's the opposite way of this. Right? The outside function is the square here. And the inside function is sine. Excuse me.
Bless you.
This is out. So when I label f and g, f of x, the outside function, will be x squared, and g of x, the inside function, will be sine x. So on this guy, the squaring is inside. On this guy, the squaring is outside. This makes a difference in the depth. And again, both of these, we know something about the derivatives.
Mm-hmm.
Okay, last one before we do some actual calculus. What are we on? It's E F. Cosine of the cube root of x squared plus 7.
Again, we'll take the cube. Oh, as our f and the g is cos x.
Right, so there's no exponent up here, right? So it's not like this problem. It's more like one of these. Right? You have the outer function is cosine,
Mhm.
and the inner function is all of this. So you would say something like f of x was the outer function, cos x, and g of x is the inner function, cube root of x squared plus 7.
Ah,
Which is fine, it decomposed, this is perfect, except, right, this answers the question I asked, but it leads me to a slightly more complicated point. I actually don't know how to do the derivative of this guy. This doesn't fit one of my rules. So sometimes you might have to decompose again.
Mm.
So this guy can be broken down again into an inside and an outside.
Nice.
So maybe we would call this, u would be the inner function, say x squared plus 7, and v is the outer function, q root x. And so what I would actually have to do to get back to where I started, just so you see this, h of x is actually a triple composition. And each one of these I can derive. This guy, this guy, and this guy. These are both power rule, and this is cos becomes sine. So I know a lot about these. But the way that this composition works is I would have to first take this u, that I call him u, and plug him in here, and then I would have to take that result and plug it in here. So the composition looks like u on the inside, then of that you do v, and then of that you do x. You do this guy, plugged into here, and then you do that result, plugged into here. F of v of u. So sometimes you will see triple compositions, quadruple compositions, compositions with 10 functions. Maybe not 10. Depends on how creative I feel. All right, so let's get to the calculus. I want to give you a kind of motivating example. So I'm going to give you two functions. One of them I'm going to call u squared, right? So y equals u squared. And u equals 3x plus 1. I'm going to ask you some hopefully simple questions, but because I'm using different variables, it might blow your mind. So the first thing I want to know is what is dy du? So what do you think this means? The derivative of y with respect to the u variable. But it's just the regular derivative, right? The derivative of y with respect to this variable u would be 2u. That makes sense? So then what about du dx? So the derivative of u with respect to the x variable, and it's just you do what you think. Derivative of 3x is just 3.
Okay.
Now what I want to get to eventually over here in part D, I want to eventually have you tell me what dy dx is. But you see the problem with that? Right? Y only has u's in it. Right? So before we can get to dy dx right now, we have to write y in terms of x's. So let me do a... So let's write y using only x's. You can. But there is a preliminary step you have to do before you can do the derivative right now. Okay? So what would y equal? Well, since y is u squared and u is 3x plus 1, this guy gets plugged in here, right? So y is equal to 3x plus 1 squared. And if I want to do a derivative, I'm probably going to want to expand this out. So what does this expand to?
9x squared plus 6x plus 1.
Yeah, so you'd have to FOIL, right? 3x plus 1 times 3x plus 1. And when you do that, you'll get 9x squared plus 6x plus 1. Okay, so I have y in terms of x now, which means I can do dy dx, the derivative of y with respect to x. What is it?
18x plus 6.
So this 2 comes down, right? If you do the derivative now, 18x. And then the x, the derivative of x is 1, so this will be plus 6. Okay, all right. That's the last last part here. So I want to do x, u, dy, du, du, dx, and dy, dx. So let me just do it for some sample values, like -1, 0, 1, 2. So let me fill out u first. When x is -1, how do I figure out what u is? Plug it into the formula, right? -3 plus 1 is -2. 3 times 0 plus 1 is 1. 3 times 1 plus 1 is 4. 3 times 2 plus 1 is 7. So when x is -1, u is -2. Now I want to know what the derivative of y with respect to u is at this point. How do I do that? I have dy du. What should I plug in? U, right? Plug in all my different u's. When u is -2, dy du is -4. When u is 1, 2. When u is 4, 8. And when u is 7,
14.
what about du dx?
3 times that.
Yeah, so now take, well, it's just 3 always, so there's really nothing to plug in. Du dx is always 3, no matter what u or what x is. How do I find dy dx? Plug it in. So when x is -1, y is, dy dx I should say, is -12. When x is 0, dy dx is 6. When x is 1, dy dx is
21.
And when x is 2, dy dx is 36 plus
42.
6. So, what's the power? How do these three numbers relate?
If you multiply and we give you
Well,
the.
it's one together again.
That's the chain. This derivative times this derivative should give you this derivative. Now, I'll write this out, okay? But what this basically means, if you want to take the derivative of a composition, right, where you have an inside function, this was my inside function, and an outside function, the squaring function. What you're going to have to do is take the derivative of the outside times the derivative of the inside. That's basically what it comes down to. Now, yeah, let me write it out, and then I'll show you. I'll come back to this for a second and show you how it applies. Specific. Let me write out the actual chain. So suppose y equals some function of this dummy variable u. It's differential. So y is this differentiable function of u, and g, and u is a g of x, a differentiable function of x. So differentiable just means the derivative exists, right? We can calculate. Then the composition y, which is equal to what you would get if you plugged this function of x in for u. So the composition f of g of x. So I just plug this in here. Then this is also differentiable. Is a differentiable function of x. And rule says to do dy dx, you have to take the derivative of y with respect to this u variable times the derivative of this u garbage with respect to x, which is what I was trying to show you there. This is fairly inaccessible. This is usually way too cumbersome to apply with this extra u stuff. Okay? So another way to write this, which we'll usually probably apply more often, is if you have f of g of x and you want to do the derivative, see this dy du comes down to taking the derivative of f. So you do f prime, but you have to put something inside of f, so you're going to put g of x inside, because that's what was inside originally. And then multiply by the derivative of g. So this part here is the derivative of the outside function. Derivative of outside. Times this part here is the derivative of the inside. So going back to the example we were talking about a second ago, so I'm going to do this in as many problems as I can in the next 4 minutes. But going back to that first example that we started with, where I gave you y is equal to u squared, and u is equal to 3x plus 1. How can we apply this less, or the one that I claim is sort of less accessible? How can we apply this back here? I want to know dy dx, so it should equal dy du times du dx. So I know dy du is equal to 2u, and I know du dx is equal to 3. But you're not going to leave your answer like this because you want dy dx, which is a function of x. Everything's supposed to be with respect to x here. So you have to substitute in. So dy dx, because you want a function of x, you would do 2, but then instead of u, you would write 3x plus 1. Now let me do the same exact problem, but without all this u garbage. Okay, because the u is helpful in stating the chain rule, but it's a hindrance in actually doing problems. It's just going to slow you down. So here's the same exact problem, but using this kind of statement. Suppose I give you the function y equals 3x plus 1 squared. So I give you a composition. What the chain rule says is you first take the derivative of the outside. So focus your energy here. Outside. And we have a rule for taking derivative of squares. Right? Of x squared, for example. The 2 comes down and you subtract 1 from the power. So to do the derivative of this square, you would bring the 2 down in front, but keep the inside the same and subtract 1 from the power. So that's the derivative of the outside. But what the chain rule says is you have to multiply by the derivative of the inside. So to match this answer, we would have to take the inside function, which is right here, and do the derivative of the inside. The derivative of 3x plus 1 is 3. So if I give you a function that's a composition and I want you to do the chain rule, I think the easiest way to think about it is identify the outside part and the inside part. Take the derivative of the outside using whatever rule you can. And then at the end of the day, you're going to have to multiply by the derivative of the inside. If this made more sense to you, you're welcome to set everything up with U's. But I don't like it.
So do we just leave it like that, or do we multiply that out?
If it says simplify, you probably multiply it out. But the calculus is done. If you want to simplify it a little, this first power doesn't do anything. The 2 and the 3 get multiplied. So 6 times 3x plus 1. And since 10, you might as well multiply it out. 18x plus 6. But not super worried about that. So at this point, it just becomes pattern recognition. All right, we're going to throw many examples as we can at you. Let's see if you can do this down. In my experience, this is one of the more difficult rules for people, so hopefully we get a lot of examples. So differentiate a function. Y equals 7x plus 1. So my mind is breaking this into an inside and outside function. Outside is this fifth power. Inside is 7x plus 1. So the chain rule says if you want to do the derivative of this composition, you do the derivative of the outside first, which means what? The 5 comes in front, right? The power rule says the 5 can come down. Keep this guy exactly the same for now. And then raise it to the 4th. Times 7. Because the derivative of 7x plus 1 is 7. So you got to multiply by the derivative of the inside. You're going to forget this sometimes.
Okay, makes more sense.
I would probably put 5 and 7 together and make it 35 times 7x plus 1. Can you put this 35 inside?
You have to, no, you first have to.
No, you would have to, if you wanted to multiply this 35, you'd have to do your exponent first, right? Exponents come before multiplication. So that would
It's
be,
not gonna be a formula.
okay. Alright, so you're feeling good so far?
Where does it begin?
We're on B.
How do you feel now?
Alright, B's alright. Everybody's okay. Everything's fine. So the square root of 3x squared minus 4x plus 6.
We'll write everything to the half.
Right, so basically you want to make this look more like one of these. Right, whenever you have a square root, you want to write half power because that works well with your power rule. So I'll write this as h of x equals 3x squared minus 4x plus 6.
Negative half.
Negative?
Half.
Oh, to start with, it's to the positive, right? So to start with, you just rewrite it as
Oh, I was
positive.
on the derivative. I was a step ahead.
Yeah, you were
So
way
sorry.
ahead of me. I think I'm way slower than that. So now when we do the derivative, we identify our outside and our inside. The derivative of the outside comes first, so the 1/2 comes down. Then rewrite the inner part. Subtract 1 from the power.
That's my negative half.
That's where your negative half came from.
Time
Times the derivative of the inside.
6x minus 4.
So do the derivative of the inside, which is power rule. The 2 comes down, 6x minus 4. This is your
Calculus is done.
You would do 6x minus 4 over 2.
Yeah, I would. But the calculus is done. So me, because I'm decent at algebra, I would go ahead and test my algebra skills out. This guy stays on top, and this guy's to the negative 1/2, so he's going to come on bottom. 6x minus 4 over 2 times square root of 3x squared minus 4x. In fact, this 2 can even cancel. This 2 can even cancel because there's a 2 in both of these.
That's too bad I already circled it.
All right, that's it. Kevin circled it, we're done.
There's no need for us to multiply the top and the bottom by
Conjugate,
square
no,
root.
no, 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 no.
I'll just write in the test, calculus is done.
Calculus is done. Unless it says simplify.
Yeah.
All right, watch out for that.
I don't know how to simplify, I'm gonna write too bad.
All right, minus
No,
1.
everything.
No.
Ooh, C. Throw some trig functions in there.
How to confuse them more. I know.
Why?
Make this harder.
Because life is cyclic, right? Everything repeats. That's why we need trig functions. That's too deep for you guys, I understand. All right, so inside, outside.
Inside, sine
Combine
x.
some-
So the inside is this guy, right?
1.
1 minus 1 over x. This is the inside. And the outside is sine. So you start with the derivative of the outside. So h prime of x will equal cosine,
1 negative
and then keep this exactly the same, 1 minus 1 over x,
times,
times the derivative of the inside.
which is x to
So you're going to have to rewrite the inside as 1 minus x to the negative 1,
1.
so that you can use your power rule. So the derivative of 1, it goes to 0, but then the derivative of x to the negative 1 will be negative x to the negative 2.
But what about the negative that's before the x?
Oh, positive.
Yeah.
Yeah, this negative and this negative will be positive. Bring it down.
Okay.
Still not too bad.
Plus or minus.
All right. Okay, so we gotta do, let's do cosine. So we gotta do these two. So we have to do cos x squared. So y equals cos x squared versus y equals cos squared x.
Oh, I'll give him 2 problems at one time.
That's right, I mean, you guys are not good.
Wouldn't it be negative on the last one?
Wouldn't that just change the unit count around here?
What?
Yeah, well, because I did the quotient rule. I combined it.
Oh, you combine these into the quotient rule.
Yeah.
So you
X
made
minus
this
1.
x minus 1 over x?
And the quotient rule came out to x minus 1. Like x minus parentheses, x minus 1 over x squared.
Oh, you don't see yet. You said parentheses, right?
Oh, yeah. I didn't know that.
Yeah, so you can do that,
You win.
but it would distribute and become positive 1. So then, it's really positive.
Okay.
I wouldn't do that, no, but could. All right, so on this guy, inside is x squared.
Then I'm done with the second one.
Outside is cosine. So you will do the derivative of cosine first, right? Derivative of the outside first.
Sine
Negative sine. Keep the inside the same
times 2x.
times the derivative of the inside. So y prime here is negative 2x sine x squared.
E.
By the way, if you don't see parentheses here, it means the same thing. And cos x squared and cos of x squared with the parentheses mean the same thing. Now, this guy, when the square is right next to the cosine, means cos x quantity squared. Right, remember that? So in this case, the outer function
2.
is the squaring, and the inner function is the cosine.
So 2 cosine x times negative sine x.
Yeah, so for y prime, the 2 comes down first. 2 cos x to the first, I won't even write to the first,
Time
times the derivative of the inside,
negative sine.
which is negative sine. So y prime is negative 2 cos x sine x. Which, if you're up on your trig identities, you could rewrite.
Or if I panic in the test again, I can just do negative
You can do
sine
product
x plus negative sine x. You know, like I'll treat it as cosine
Times.
x time up.
Times.
Yeah, and do the product rule.
Yes, you could do the product rule on this. Which is why I'll probably put cosine to the 30th.
No thanks.
Then I'll see you on your test. It'll be 30 cosines right now.
Whatever.
That was,
And he's laughing about it.
Oh, I'm rolling on the
He
floor.
enjoys it. Oh gosh.
All right, so let's do 7 secant root x. 7 secant of root x.
So the 7 we just don't want.
7's a constant multiple, right? So when you're doing the derivative, this guy's just going to follow along. Right, so the 7 you can kind of ignore as long as you bring him down, right? Because he's a constant multiple. The secant root x is the real problem.
Secant x to the half.
Yeah, so we can definitely rewrite the root x as 1/2 power. So 7 secant x to the 1/2. Then we have to identify our inside and outside. Right, so inside is x to the 1/2. Outside is the secant function. So the way the chain rule works, you do the derivative of the outside first. So h prime of x equals, do you remember the derivative of the secant?
secant x tan x.
Secant x tan x. So in this case, because the inner function is x to the 1/2, I'm going to have secant x to the 1/2 tan x to the 1/2 when I do the derivative of secant, or the derivative of the outside. And then the 7 follows down. But, not done, right? Times the derivative of the inside. So times, you do the derivative of the inside with the power rule. 1/2 comes down. X to the subtract 1 from the power. Yeah, so we'll have altogether h prime x equals 7 secant root x tan root x, over 2 root x. Can you cancel this root x and this root x?
No.
No.
God, no.
Present sound.
Yeah, he's trapped. It's like a force field, it's purple force field. Ooh.
You can't go home.
It's that he can't go home.
No, you said that like Monday or something.
Yeah, I see.
If that were 7x.
Yeah. X out here.
Then you have to do the product.
Oh, absolutely, yeah. Yeah, definitely. So we'll get to some problems where we mix the chain and the product rule. But yeah, if this weren't a constant multiple, if this were 7x, then we would have to do a product rule first before we did anything else. Good eye. Come on, delete that. So let's try to mix these in. So suppose I gave you our y function is the square root of, let's do x times sine x.
Put everything to the half again. Or we can split it, like x to the half times.
Yeah, so you could split it up and do x to the 1/2 times sine to the 1/2, or you can put it all to the 1/2 power. Either one is
Yeah.
probably going to be about the same amount of work anyway. So what I would do, I don't know, I would do chain rule, right? Because I have an outside root x, and I have an inside x sine x. So I would do this guy's inside, and this root is outside. Or, because we don't like roots and we like 1/2 powers, we could do it like this. Which is going to make the derivatives a little bit easier to think about. So this is the outside.
I don't know if I did it right.
So chain rule says y prime equals
Half.
derivative of the outside, so the half comes down. You rewrite
X
x sine x to the what though?
negative half
Negative 1/2, right? Subtract 1 from the power.
times 1 cosine x. Oh, what did you do?
Blew my mind. Okay, so times the derivative of a product. How do you do the derivative of a product? Product rule. Yeah, so you have to do the product rule on this, right? So if we do the product rule, you would do the derivative of the first times the second plus the first times the derivative of the second. So this guy is f prime g plus f g prime.
Sine x 6, 2, 6.
Yeah, so y prime equals sine x plus x cos x over
2 root x, sine
right, this guy goes to the bottom and there's a 2 on the bottom. So this was an example of a product rule inside of a function, right? So a product rule inside of a chain.
You're getting really lax on your G problems.
Oh, well. Because it's slightly easier than limits, I guess, huh? Just processes. Now I could do a product rule outside of a quotient, or of a chain rule. So h of x equals x squared times cos cubed x.
That's easy.
So the difference here is the product is the outside, right? There's not an overall function outside. The product is the outside. So you start with product rule here. You start with f of x equals x squared, g of x equals cos cubed. Then you do your derivatives just like you would for product rule. F prime of x is equal to 2x. But then inside of the product rule, because we have a cos cubed, there's a chain rule. G prime of x, remember how this guy works? This is cos x cubed, like this.
So 3 cos x squared.
So this is the outside. This is the inside.
6 squared.
So the 3 comes down. Oh, green not. 3 comes down. The cos x remains the same. Subtract 1 from the power. So there's the derivative of the outside. Times the derivative of the inside. Negatives. And product rule says we multiply these.
2x to 7q.
So let's see, we have x squared times, oh, actually, let me start this way. 2x times cos cubed x plus, since it's product rule, x squared times 3 cos x squared times negative sine x. So here's your derivative. Calculus all.
Calculus is done.
Yeah, you can stop. You don't have to.
I'll probably clean this up a little.
No, the calculus is done.
So this is negative 3x squared. And then cos squared x sine x. So you guys see the difference in these two problems? All right, how we started with the chain rule here and then applied the product rule. Here we started with the product rule and then applied the chain rule inside. So in previous classes, people have had problems telling us where to start with. So let me know if I can fill in. Okay. So yeah, let's do 2 more. Tangent y equals tangent of x over x plus 1. So what do you think?
Bueno.
Secant squared.
Bueno.
Secant squared, right?
Yeah, so I would do chain rule first because this quotient is inside. Right? So I have an outside function and an inside function. So you start the chain rule by doing the derivative of the outside. Y prime equals the derivative of tangent is definitely secant squared. Inside of the secant squared, you put the same exact thing you have.
X over x plus 1.
Then the chain rule says multiply by the derivative of the inside. And the derivative of x over x plus 1 is a quotient rule. So you'd have to do f of x equals x, g of x equals x plus 1. The derivative of x is 1. The derivative of g is 1. So then we multiply across.
X times x plus 1.
and then divide by g squared. So let's write it here. Derivative of the top 1 times the bottom, x plus 1, minus the derivative of the bottom times the top, so x times 1, all over the bottom plus 1. So this is your derivative of the inside. Oh,
Calculus is done.
calculus is done. So if you do this problem, by the way, on a test for me, and you forget to put this in for some reason because you're high, or I don't know how you guys do this, but you don't put this in, you're going to lose, if not 3, definitely 2 out of the 3 points.
You mean the g squared?
No, yeah, this whole, no, this whole the chain.
Oh, yeah.
You know what I mean? People just say, oh, derivative tangent secant squared, and then they forget to multiply by the derivative of the inside. That is a big, crucial, terrible mistake. Loved ones will die. It probably cleans up a little bit, though. Right, this is an x plus 1 minus x, so it'll just be 1 on top. Prettier. Yes.
Divided by.
Yeah, okay. If you wanted to, that's fine. Secant squared. This can come off. Oops, you wanted to do this. Remember, this guy's stuck inside the secant. He's never gonna do anything with this guy outside. Alright. So that was what? The quotient rule inside of a chain rule? Let's get to something else on here. So sine squared of root x cubed plus 1. Since people were complaining that my examples were not difficult enough. So let's call this y.
Double chain.
So we can put that 2 outside everything.
Right? So this is the same as sine. Let me change this to the 1/2 power while I'm at it. So sine x cubed plus 1 to the 1/2, all of this raised to the second. Do these cancel? No.
Because that's inside the nickel.
This is inside, this is outside. So my outer, when I start applying the chain rule here, my outermost function is going to be what?
2.
So this is where I'm going to start. So there's kind of a cascading effect. Do the derivative of the outside first, so 2 comes down. Rewrite the exact inside, sine x cubed plus 1 to the 1/2, all to the first power, so I won't even write it, multiplied by what? The derivative of the inside, the derivative of all of this.
Which is going to need 2 steps too.
At least.
Wow.
Steps.
So now to do the derivative of the inside, you have to break this guy down. Here's your inside. Here's your outside.
No, the inside is just the...
You okay? Does that make
Yeah,
sense?
it's not. It's not my
So
data.
times cosine.
So this x cubed plus 1 to the 1/2 is inside of the sine function. So we now have to break this guy into an in and out. In, out. Okay, so the derivative of sine is cosine of, keep the inner the same, oops, to the 1/2. Times the derivative of the inside. Okay,
Half,
so now we have to do the derivative of this guy.
half,
1/2.
1 over.
So this is the out.
mhm.
So the 1/2 comes down.
Then
Write the x cubed plus 1
negative
to the
Negative 1/2.
-1/2.
time
The derivative of the inside, which is finally simple enough that I can do the derivative.
3x squared time, just kidding. That's it for now.
Still circle that. Those brackets don't really mean anything.
Okay. I hope that's all you had.
That was a pretty
No,
big
wait.
J problem.
That was a pretty weak J problem. That was more like an F, huh?
Yeah.